Okay, everybody. So it's about time to start the lecture. We do have our own Lathe DerDrache finally giving their lecture on high precision engineering. Lathe is one of the earliest members of DGen Tech, and I actually wanted them to give a lecture for a while. Apotech vouched for them multiple times, and I'm glad they're finally able to do it. Very cute Derg, very interesting person who does some pretty interesting work. They did make this a pre-recorded lecture, so that was always allowed. By the way, if anybody else wants to give a pre-recorded lecture, it doesn't have to be live every time. Now, once again, for the housekeeping rules, this stage projects the voice. This also is a voice projection tool, so please stay off the stage. If you guys want to have a lecture conversation during the lecture, please go in one of the back corners or the spawn area, so you don't interrupt the people who are listening to the lecture. Thank you very much. Now, final check. Apotech, are you ready on your end? Okay. All right, let's get this thing started. And everybody sees the video, right?
Maybe not.
Yeah, nothing's moving yet.
And welcome to my little
Oh yeah, now it's good. Yeah. Can't hear anything.
We'll today go over
Yeah, the audio's out.
who am I
Audio's too
with
quiet.
this little Dirk
You
here
gotta
in
increase
front
the
of
audio on
your
your end.
screen talking to you right
yes,
now.
oh, sorry, thanks.
Yeah.
What
of
is
course.
actual
In a
machining?
noisy world.
What is the definition about it? What is the right hand rule we use there? Why is it different to like Blender or like Unity? Type of machines we have. What I'm using, for example. What is the difference between precision and accuracy? A little rant I put in there because why not? We love a little bit of ranting. And a little bit about the methodology which we use in the machining world. More likely, but in the machine methodology itself, less than about parts. The part methodology part of it. So I am Lathe DerDrache. I live in Germany. I had an apprenticeship as a machinist. I specialized in the milling part of machining. I am in this trade now for roughly around 13 years, a little bit more now since I made this little presentation. I'm since 2 years now moved into the high-end ultra precision field. Is prospectively in the high precision I do machining pure beryllium, and in the ultra precision part I'm making mirrors. I will not go too much in both of them. That's way ahead of the start. It has a part of it, but there's not deep dive into this. I'm doing next to machining also the programming for machines and also do metrology work. And I'm very bad at making presentations. I will stumble over words and please forgive me if it feels a little bit rushed or something. Okay, what is machining? Yeah, machining is a manufacturing process where the desired shape of a part is created using the controlled removal of material. That is a roughly very right description about it.
I think it is time to write.
I don't go in when it says about most of metal, as we can see in Wikipedia is described, which is not true. We do also plastics. Wood, on the other hand, is more described under woodworking. There are some bigger machines that do a lot of wood stuff, but it's always specialized in the woodworking field and doesn't take a part in a lot of like more metal and plastics machining world. And we see 3D printing uses additive manufacturing, while machining is always subtractive. We always remove material in machining world. We don't add to it. There are some specialties about it. I will come to it a little bit later, why also 3D printing is in there. But usually when you have something 3D printed and you do machining it, you only do certain surfaces to get specialized surface properties or like shapes you cannot create with 3D printing because 3D printing is not a very precise process. No. The right hand rule is used in the machining world to define your axis the machine runs in. It is a little bit different in the way how it sits compared to people that use Blender or Unity. Everything you see is like the z-axis is flipped or in complete different ways compared to machines. The right hand rule basically takes, you use your right hand, you point your thumb out, your index finger out, and your middle finger points up, which is not easy to do in VR. And basically you then have your thumb is your x-axis, your index finger is your y-axis, and your middle finger is your z-axis. And they all point into the plus direction. And it always view from you over the hand. How you hold it, this is how the machine axes are set up. From the point of view where you like control the machine. It can have differences here. And not everything is standardized, of course, because everything having a standard is kind of boring, some manufacturers think, and make your life kind of horrible if you're not be careful and look into your machine, how it's set up. Now, what types of machines we have? We have milling machines. That's the kind of thing I am specialized in. We have turning. They're actually called lathes. That is where my name came from. I'm very much like doing this machining work, and I'm not very creative when it comes to names. So we have some old shaping. These machines are not really built anymore, but they still exist. And we have grinding. That's, by the way, a rough view, and it's the more bigger one you will come across on YouTube and then on the internet. Is this kind of things. So, what does a milling machine do? It's basically, you can create a 3D symmetrical and non-symmetrical parts. What does this mean? You have a part that is any shape you need, round, a block, a rectangular, a triangle, you doesn't care, and you just remove material in a certain part. Always the key component of our milling machine is the tool spins, the part is stationary, in quotations. It's depending on how the machine is built, it's a little bit different, but always your tool that removes and cuts spins in a milling spindle, which is, for example, on this machine up here, and here's the tool holder with the tool in it. That's how it's set. And here we have it, a more complex machine with also the tool is here, and here's the spindle. And every milling machine has at least 3 axes. You have always an X, Y, and Z axis, which is, for example, this machine has. You can have something like this, that's a 5-axis machine. You're adding 2 rotating axes to it. Like in here's a rotating axis and the table rotates to make more complex parts and more complex shapes. Next, we have a lathe. We call it actually a lathe. The process is called turning. Don't ask me why milling and milling machine is the same, while lathe and turning is differently. Somebody came up to it. I'm German. For me, it's different. Okay, what we have here, the difference is the part spins. Now you have a stationary tool and the part is spinning. And you're basically pushing the tool into your part and then it cuts. You have usually 2 axes. You have an X and a Z axis. X is the diameter and Z is always the length. You can have also, like we see here, a more complex machine with more axes. We come to this a little bit later because that is something special over here again. But usually you have 2 axes, you don't need more. And every manual machine basically has 2 axes and has handwheels, you move it around. This is usually how a CNC machine looks like. And we have, I added now both together because this is not my world. I'm not part anyway of grinding. I can do a little bit about it, but it's not my specialty. And shaping, I did this in my apprenticeship, but it's kind of old. You have basically the tool, a little cutter set on a moving arm or slide, and it just slides over your part and you cut with it. So you push the tool into the part. It's a very old process. They can do massive cuts, but you usually don't use them anymore. They're all manual, nothing really defined. They out of fashion. You still see them in some shops, mostly likely seen in for apprenticeship because it's nice to teach younger people on all the stuff. Especially can learn how to grind cutters on it. These machines are very sturdy and forgiving, so they're still kind of nice. And they do a motion that is very much liked in the furry fandom. You can do a lot of bullshit with it. And we have grinding. This is usually a very precise process. And till the last 5 years, usually people would say, everything you need very precise, you grind. This kind of trend is going away, but it is still a major thing, and still certain applications need the special surface they do on the grinding machine, because the grinding stone does different surfaces than a mill, an end mill, or like a lathe tool. But I cannot go into deep dive into this. It's not my specialty. I'm not really known into that. No. And then we have hybrids. What are hybrids? Hybrids are usually a mix of both. As we see, we have mills and lathes together as a turn mill or a mill turn. The why this is two different names but describe the same thing is special here. You usually have, like for a turn mill, you have a lathe that can also mill. Like you have a driven tool which can also spins now. You can have an end mill or ball mill or whatever in there, and you can run it through your part. And on a mill turn, for example, it's usually 5-axis machines. You can put a normal like lathe tool into the spindle. The milling spindle gets locked, and your table rotates, and you can cut with it. But what's always important is the first thing that's called out, like on a turn mill, the turn part, that's the main thing the machine can do. The milling part gets added to it. It's always a thing they can do extra, but not very well. The same thing for the mill turn over there. It can do milling very well, but turning, it is quite limited. It can do a lot of shit, but you cannot do like heavy cuts, which on the size of for a mill turn, what you think, oh yeah, I can do a lot of heavy cuts, but it is limited in what it can do, because size is completely different and the way how it is set up is completely different. Which we can, when we go back here, this is a turn mill. It has two lathe spindles, turning spindles, which is the main application. You have a turret down here for the tool holders, where you have lathe tools in there. We have some tools up here that's called a gang style tool system. And up here we have a milling head. That is called the universal milling head, because it can rotate. It can go into both sides. It can position itself, and it has a milling tool on it. But the downside is always, these machines are not made for parts you can usually do on here. You have here a nice big table. The machine axis, the linear axis, have lots of travel. No issue to get everywhere. On a machine like this tool head cannot move a lot around in the y-axis field. So you're quite limited on what can it do. And it's not very strong, because your lathe spindle that can spin very fast has to hold the part then stationary, or use as an indexer so it can rotate the part while it's milling, and they don't have a lot of torque. So you cannot do heavy cutting on it. They specialize also the milling spindle, usually not quite powerful, so you cannot break your part. It not starts randomly spinning because the servo stops working and errors out and loses all control and like cannot hold the part anymore. Now, Also what we have is grinding and shaping getting added to milling machines or also lathes. The shaping is pretty easy. It's not complicated, especially on a lathe. You can do it on a manual lathe too. You're just having a shaping tool and you push it with the Z-axis into your part. Or in the X-axis when you have a side slot. You don't even need driven tools for it. You can do it with a simple manual lathe already. If it's stable enough to handle that, and you can lock the spindle to not rotate. Grinding, yeah, there are some people that make grinding attachments for the manual lathes. You can do it on a milling machine too, but usually manual milling machines don't have a lot of high RPM, which you need on grinding. And grinding is very deadly for your guideways. You have grinding dust on your guideways, you run over it, you have steel on steel with grinding dust in between, and it will destroy everything, and your machine is total after. But it's possible, and a lot of machines get grinding at it. The milling machine I'm working at work can do grinding. I have grinding systems on it. So that is a new thing today, especially on 5-axis machines, because you can do then 5-axis jig grinding on it. And this is also a thing that gets added now. 3D printing. There are different ways of it. Usually it's the SLS time, so selective laser sintering. You shoot powder and a laser beam on top of it, and you just grind, building it up. It looks like FDM because there's no powder bed and everything. Has the same issue as grinding. Your guideways will die a lot because you're shooting with high pressure dust into it, which should then melt. And not every dust gets melted, it flows around and it can be a mess. So it is not seen a lot. There are a lot of machine builders that have at least one machine there that can do printing. Yeah, not a lot of people will get it. It's also very expensive to get. Because depending on the process, you need specialized like laser sources or high pressure systems. There's some 3D printing that just shoots out the little powder, the metal powders in high speed on the part itself, and it locks into by bending the corn itself, the little particle. Yeah, I never worked actually with anything about it. I only saw it. I cannot tell much more to this, other than you get it only when you really need it, when you want to spend that money. Okay, now precision and accuracy. It's both very important to know what it is in the machine world, because you will run with both. And usually they're both measures of error you have. Accuracy usually describes you have a set point where you will land, like a distance, a hole size, a diameter of your lathe part. You always want to hit that, and how far your part is describes how accurate you hit your target. And the precision is on when you make a lot of parts, how much you fluctuate around, so how much the machine moves and changes this set measurement. You usually want the precision very small, so very tight, and the accuracy very nearby where you want to land. The big thing about machining is usually we don't directly care about accuracy problems because you can fix that. You can adjust the machine, like you adjust an error table or something, you can move it over. Precision is the different thing. And by the way, every machine should be accurate. If not, don't buy a machine. Give it back to the manufacturer, and it cannot move to a certain target. Precision is a thing that will always fluctuate because it has a massive influence on everything around you, can influence how precise a machine is. temperature, humidity, the hardness of your parts, how the tool life is, and how long the machine did run already, how old it is. Everything will change this all the time. And a very expensive machine can already from the beginning have this very tight. And then it comes to the person in front of the machine to get it even tighter. But you will never have a zero value there. You will never achieve it. You're always getting to a smaller digit. But yeah, that is basically the description of precision versus accuracy. Oh, and now coming to my little rant. False advertisement in the machining world. I hate this very much. And a big problem is, this is not a thing in the professional world. This is a thing in the hobby world. And it's a very big problem because of something like this. This is a machine of, sorry Precision Matthews, but I saw a video about this machine and it's called Ultra Precision Variable Speed Milling Machine. This should be an ultra precision machine. I look at this and say no, it's not. It is not even a high precision machine. It is maybe a precise machine, and from what I saw, it's not a bad machine overall, but it's wrongly advertised. And we see it also, they don't call everything high ultra precision, they call it now high precision. And what the fuck? It's my thing about it. At some point they call it even run out of the spindle. The high precision spindle is 5 microns, which for a high precision machine is a hell amount of lot for run out of a milling spindle. You should not see 1 micron run out if you want to do high precision work. And contraire, this is an ultra precision machine. This is actually also the machine I'm working on. Not directly the machine, but it's a picture of the manufacturer of this machine I'm working with. This is how an ultra precision machine looks like. With a very old CNC controller, which is kind of funny. This machine works in the nanometers. And to show you that, you have here the data sheet of the machine. And you know, the Precision Matthew machine says they have a 5 micron scale on it, like the normal vernier scale. These machines have picometer scales and motion accuracy of less than 25 nanometers. So every motion this machine does is smaller than 25 nanometers in precision. You don't see that on a high precision machine or a hobby little machine. You even touch it and this number goes high. Same is for the spindle. It's an exiradial runout of 15 nanometers. Contrary to the ultra precision Matthews machine with 5 microns. This is 15 nanometers. For people that don't know, they are not usually known what is the metric scale. 1000 nanometers are 1 micron. So 15 nanometers are 0.015 microns. That is a hell amount of small number. Also in here, 0.6 microinches. I don't know what 5 microns are in inches. I'm sorry. And also very important fact, temperature controlled 0.1 C accuracy in the liquid cooling system. Also I want to point out, this machine only cools the spindle up here, which is this little thing here. Everything else is not really cooled. You need a very stable room temperature to actually use this machine. Otherwise, and I can really say this out of experience, you will have a shitty time machining with that if your room just gets hotter about 1C in like 1 hour. You have really big problems with that. Oh yeah, here we have the linear axis. We have a position and feedback resolution. So we have linear scales built in. It can read it out from 8 picometers. That is very, very small. To see behind it, it's 8/1000ths of a nanometer. It is fucking small. It is smaller than all the little bacteria and viruses the world has. So you basically sneeze on the linear scale and have a virus on it, and it will have a bigger impact on this number than the actual scale can read out of it. It will have problems reading it. And of course, the straightness of the machine, that is ultra precision machine, they're very straight, 0.3 microns in the fold movement. But that is right now, we don't go into it. I was thinking about it, but I think that goes into too far. And there's something else that came up. There was a machine in India from Nimbus. It's a 5-axis machine. There was an article about India goes into the high precision area and so forth, which I still today think this article is paid by these makers, because I don't think that India is not already buying machines from Germany and stuff and can do already high precision stuff. Because everything I read in this here, especially when you look up here, 4 microns linear positioning, any tight positions can be maintained within 4 microns. What is this? This is not even a standardized testing. They just describe it. This is the resolution of the linear encoders, of the linear scales they read out of the position of this machine. They cannot go higher accuracy. It doesn't describe precision at all. And they describe it around here. 5 micron linear precision and 5 arcsecond rotary accuracy are achieved with on-axis feedback linear scales on X, Y, Z, and dedicated rotary encoders on both V and C axis. So the numbers on paper match the numbers on your QC report. That's quality check report. So basically, you're making a part, you measure it on a measuring machine, and it will tell you that you're within 4 microns. That is not true. This is false advertisement in its finest. Don't trust anything that has described anything like that. Also, it should always state something about DIN ISO or like about whatever America uses as a standardization system, and the test how they measured it with this standard, which is also not the highest precision thing. I will come to it a little bit later. And yeah. And it says a loop inside plus minus 4 micron. It isn't chasing a benchmark, it's grading one. We have seen earlier the high precision, ultra precision machine. Plus minus 4 microns is a joke. Even buying a Haas machine should be able to at least getting an accuracy of plus minus 4 microns, if not even better. And Haas machines are, as in the machine world, the cheapest option you can buy. RK machines, I will not go into too much about that, but every other machine, they have about the standardization DIN ISO code plus minus 2 microns. Precision accuracy, this is nothing else of a benchmark. This is a joke in itself. So yeah, false advertisement. I hate this stuff. I don't like to see it, but there's always somebody you can fool with it. Good thing at least is this machine apparently is not to buy. It's just a one-off test thing. I don't know why you even then go on with that if you cannot even buy it. And yeah, I have to quickly break this entire lecture to explain a few things. Actually, one thing. I'm talking the entire time about high and ultra precision, but I never explain what it means. And explanation nobody knows. Actually, there is no predefined definition about it. There's nothing nowhere stating what it actually means, but there's some kind of ways how the industry kind of defines it. Normally, when you talk about something, it's precise, it's a precision machine. We say plus minus 5 microns is possible to hold over a long time in a lot of parts around it. It's not always there. Parts can have a bigger spread and everything. But yeah, it's around 10 microns. At high precision, usually can say plus minus 1 micron or plus minus half a micron, where you can easily say, okay, this will work around. And ultra precision is everything down there, everything lower into the nanometers area. Some ultra precision machines can easily reach like 10 nanometers of long-term precision, more like actual precision, less precision on a part, which is a completely different thing. But so you know what I'm talking about. I'm sorry that I completely forgot it to add it actually in the lecture, but here you have it. Wow. Okay, and now we go a little bit into the methodology part. I explained to you why this is important, why you should not trust a claim that is just saying it is like that. I will not go into deep dive enormously because I know about a little bit things about the metrology work and how you're measuring in accuracy and precision of a machine, but I'm not really well into it, and I cannot explain anything. I don't even know the DIN ISO standardization code it uses. So, but I can explain why it's important. And we saw it earlier, why measuring is important. First things first, we have the two usual things every good machine maker uses to test a machine. We have, on top of it, we call this a ball bar test. You have, let me go up, we have a little magnet stand on your table with a little bar in between that has two balls, and you have a fixed tool holder which has also a little bar with with magnets in it. So basically this little bar in between, this black piece up there, that is a little linear encoder. It measures distance between this fixed on the table and fixed in the spindle little holders. And what the machine does is you make little full 360 degree arcs, so radiuses or diameter movement, usually around 100 millimeters, but you can also get bigger ones and smaller ones depending on the size of the machine. And you measure with that basically how good two axes of your machines are working together, how good they are like synchronized to each other. And you're then getting a little graph out on how round the machine can actually move. You can also get like little errors, like when you have a machine with a ball screw or a normal screw, when you move in one direction, the ball screw turns in one direction, and when it has to go over the arc, it has to go in the different direction. And you always have a little bit of delay in this movement when it changes, and you can measure it with that. And you can correct it. There are machine software solutions to correct this behavior and to correct errors out. That's why you do this, or should do this actually every year or every like 2 to 3 years. You should do this. Not everybody does it, by the way. So you usually get this done by the machine manufacturer. They set up the machine in their building after they build it up and test it with that. And the next big thing is this little thing. That is basically a laser test. You have basically, this is more like a laser interferometer. And it basically, you have this outside of the machine mounted laser source and receiver. You have a little mirror block, and you have another mirror mounted on the spindle or on the table, depending on what's moving on the machine. And basically, this little system receives a piece of the laser from this one and from this one and uses interferometry to basically measure distance. Somebody with actual knowledge in optics can potentially explain this better, but you measure linear accuracy of your linear axis. So basically you move to different positions and you measure the distance then, and you can then see how much error you have in your screws. And you then can use software again to map this error out. You scribe in, and like every 50 millimeter step, you make a stop and read out, and you can have a little like Excel sheet in the machine where you describe it at this 50 millimeter position. You were this out of position, and describe it in the machine. Software then can compensate this error. This is the two main things every machine maker or every good machine maker does, and this is described in standardization codes when you buy a machine. It's also, if you want a high and ultra precision stuff done, you do this after the machine is delivered to you and is sitting in the position you want to have the machine then. Because every movement of this machine, every time you have to lift up a machine to move it around, it will bend and flex the entire machine bed, and you have to do stuff like this. And yeah, that's it. That's a little bit thing. Maybe at some point I can go into more deep dive into metrology stuff about machining when I have more knowledge. Give me 2 or 3 years maybe. Otherwise, you can now ask questions for the people in the US meetup. I most likely will not be there, so you can ask the questions and the team of DigiTech will write it down. And most likely, if I can do on the EU meet, I will be there and I will answer these questions. So go on. I will be out of here now. Have fun and have a good day or good night or good morning, depending on your time zone. Bye.
Okay. Thank you very much, Lathe, for that lecture. So now will be the Q&A section. Lathe, as a reminder, please, for audio reasons, please repeat the question that's asked. Now, we did have one question that was recorded yesterday, or made yesterday. I can't grab onto this while looking at it. We had Mako Fox. They asked the question, after we graduate and no longer have access to a machine shop, what is the best way to get custom parts machined? Do machine shops do that? Hobbyists? If so, what details would they appreciate for a custom job? And I'm going to add on, do you do custom work? And don't forget you have to trigger it.
Doesn't it work already when I'm staying here?
No.
We've had some issues. Yes,
Broken.
but not consistently.
Okay. So, to answer that question, yes, there are machine shops out there that will do custom jobs, mostly that are chop shop work. If that's really the priciest thing, I don't know. Usually chop shop jobs are very expensive because they usually want to do business to business work and not business to customer work. They could be that they going up to very pricey. They more tending to like high amounts of work, like you bring in with 100, 200 pieces. That's more their liking. What's more feasible is going to something like JLC 3DP. That is the manufacturing side of JLC PCB. You can just upload a CAD model, like a 3D file, and send it out together with a drawing. You have to make a simple drawing which shows important distance or measurements you need and also tolerances on it. You can do normal precision with it. That's fine. They will do it fast enough and good enough for what you need. And they can also provide you with way more special like surface options than anything. On other hand, if you need high precision or the precision stuff, you have to go to specific companies for that. And accept that it will get very, very expensive. That is sadly the sad truth for it. You will not find anywhere in the world a really shop work who can do it. Hobbyists can do certain things depending on what machines they have. You can look into on the internet if you find hobbyist machinists who do that, or depending on the area, you have some like clubs, people that come together doing that stuff and having a small shop where they can do stuff. You have to look out on that on the internet. I cannot do help a lot. I do sometimes do shop work, but I'm in a very expensive field, so I cannot tell you I will make it for you too cheap. I will take at least 100 euros an hour for work on that. Okay. Other questions?
Okay. Yeah. Okay. Yeah. So just come and grab the.
We have one written on it. Can you make a CPU with this type of... No. That's completely different area. Okay, good. You want it? Can just say it. I will repeat it.
Oh, okay. What software do you use for making your G code for the CNC machines?
What software do you use for making the G code? It is, for what I'm personally doing right now at work, is Hypermill. My previous job, I used Autodesk Fusion, which is mostly known in the hobby field. Also very good used nowadays on also professional work. But if you have to do stuff that is NDA, you cannot do it in Fusion because of cloud-based. You have to do it on everything that's offline. So Hypermill, it is. Sadly. Other questions?
Yeah, Lathe, question for you. Can you hear me?
Yeah. I can hear you. Your question?
You mentioned that the machines get less precise as they run. What happens? Is there anything you can do when they get too imprecise? That's the first question. Second question is, how is there ever a time where you have to have the manufacturer come out and remeasure machine more than once a year?
So when I don't understand, right, you're asking what you can do to keep the machine precise, and then how often they come out to make sure precise.
Yeah, so
every
as the machine gets, as the machine gets less precise, is there anything you can do besides buying?
To keep the machine precise, every machine has a maintenance book. So you have like something to do every day, every week, every month, half yearly and yearly. That's usually also implies that the machine maker comes out yearly to make an actual checkup. Most machine shops don't do that. They do not always even the normally like monthly, weekly and daily maintenance. They just let it get dirty, dirt pile up in certain areas. It will destroy very important surfaces, and they only can get people in when it's too late. But if you keep the machine maintained, you can actually keep it running. And if you're getting, usually don't need to yearly get the machine maker in to let them check it. If you do it every 2 to 5 years, it's mostly enough when you're doing very, very good maintenance work. And then it's only to check up if it's still to spec. And if it's out of spec, the machine maker will replace certain parts on it to get it back to spec. which is normal. You have always some wear on certain surfaces. So,
All right, thank you.
to the question again for the how often they come out, it depends. I cannot really tell you that. It's mostly 99% of what service technicians do from a machine maker is repairing machines because somebody crashed it. That's 99% of the work, sadly.
All right, thank you.
Other questions? Oh, can you make a better Tesla valve than with a 3D printer with this? You can make one that is actually tight for gases and stuff compared to what a 3D printer can do. But a 3D printer can do way more complex geometry than a machine can do because you still need space to get in with your cutter. But yeah, it depends on your shapes you want to do. Yeah, you can combine stuff with that. Yeah, you can combine 3D printing with machining, which you can do with hybrids, or you just let something 3D print and you machine it then. Okay. More other questions?
Not a question, but an answer for the first question that you answered. One website that you can get in contact with small businesses or people is Exometry.
Yeah.
Exometry gets you set up.
Oh, yeah.
Talking with one person to a seller, so you can be a person who has just a mill or a lathe in your basement, and you can put your account on Exometry and get jobs here and there. Or if you just need 1-2 person jobs, you go to these people.
Oh yeah, Spike just said it's Xometry is out there that is basically like a marketplace, you can say, for machine work. You can find machinists in there and companies can put out what they're doing and can find customers. That's also existent. But
right. You mentioned in the intro, a pre-recorded talk, that you wanted to say something about the reason for the particular coordinate system that's used, but I don't think that came up again.
oh yeah, forgotten it's why I didn't mention it. It's most likely I forget it that I forget to mention why different coordinate systems are used. To make it simple, it's sometimes depending on the machine out there. Some machines are built to do certain movements. So what they do, they get out of the typical right-hand rule and flip coordinates around to fit more to what they need and what they have to do. And you have some machines maker, they give a complete shit to say what normally is done and they make whatever they want. It also depending how many axes you have, you can have normal X, Y, Z axes. You have then like U1, U2, U3, and you're going into numbering theme, and it gets quite complicated over time. But most people stay to the right-hand rule and to make it more normal, and people can just easily switch between around it. Yeah. Other questions? Have someone tried to make a milling machine with another milling machine? Like, yeah. I mean, that's usually what you're doing. You have machine makers have massive machines. Like we're talking, you can drive into the machining area with a truck, literally. They're massive, and then to make their a little bit smaller massive machines. So they cast like the entire frame, put it in, and machine all the important surfaces down. Yeah, everything is done on other machines. All your ball screws and everything is done on other machines. An entire machine is not possible in one go, of course. But you make all the parts on different machines. That's quite normal. Except you're like a Taiwanese machine maker who does also a lot of handwork to the machines too. But that's a different thing then, to get higher precision. Another question? For the people in the back, if you have question, please come forward. I don't see all the people in the back, so if you put your hands up, I cannot see it. You're all invisible for me.
I don't see any hands raised in the back.
Okay, then I guess nobody has another question here. Anything else maybe you want to know?
The CNC systems with grinding as an attachment to the CNC, how do they prevent the dust from getting to the guideways?
So to prevent the dust from grinding on a normal milling or
Yeah.
lathe is funny enough, most machine makers don't do actually more than they normally do. They use normal like bellow systems or like having a sheet metal that just on the side is closed up and can move around. It is a little bit downside and yeah, it can lead to issues. That's why you should never grind dry without coolant, because you don't want the stuff anywhere else. But usually the coolant can keep off the grinding grid out of it. But I would say the bigger issue is with hybrids machine that can do also 3D print. They have bigger issues because you have no coolant anywhere. That stuff, I heard that machines like that keep like 1 or 2 years and you have to replace a lot of parts because they grind it to death. Okay, another question?
Yeah.
We have one that gets written right now, and I have seen people doing search with CNC. Yeah, you can, when you have a PCB which is completely copper, you can just cut out copper to make traces. That for that there actually exists tabletop desktop machines to do that. Funny enough, with highly complicated PCBs to mostly flipping around, yeah, you can do that, but nothing with like 10 layers, you cannot do that. You need to actually then, except you're good at gluing stuff together precisely. I don't know.
Yeah.
Okay, question?
Yeah, for the very high end of ultra precision machining, what would be some applications that actually need all that precision? Because you're getting into the sizes where it's much smaller than even wavelengths of visible light.
Yeah, what do you need high or ultra high precision or ultra precision machines is mirrors. You're displaying wavelamps. That's the ultra precision machine I showed in the lecture is actually a so-called DTL, a diamond turning lathe. It is only there to make mirror surfaces, nothing else. That's the main reason why these machines exist. They have such perfect movement that you can usually go down into the single-digit nanometer area of surface roughness, and also form shape depends on how big the mirror is and how complicated. But you can then make mirrors like you need for infrared stuff or visible light. I would not say you can do the mirrors for the James Webb microscope. That is very, very more flattened in the surface roughness than a DTL can achieve. You need them to actually grind that stuff down. Yeah. More question? Can you make spherical mirrors? Yeah, you can. Normal DTL can do freeform everything. As long as you can reach it with the tool, you can do it. You can do single lenslets and whatever you want, depending on if you can fit it still. It's mostly size that limits you, and not the shape directly. Also, there are special details also only there to make your inserts for your eyes. That's also existing. That nothing else do to cut little simple plastics to do that. You then squeeze into your eyes to see better. More questions? I guess that's it then. So
Yeah, I don't see any on the stream.
yeah.
How do
So
we
then,
clap?
thank you for being here, and I give it away to VTEX again.
Controller smacks.
Thank you all for joining for this. If, of course, Lathe is part of the community, so if you have any additional questions or need the help of an expert in high precision machining, we got one right there. So go talk to him. All right. After this, we're going to be going to have a casual movie viewing of the movie Primer, and we'll do that in like 15 minutes or something like that. So this is the end of the formal portion of our meetup, but we're going to still be hanging out. Please feel free to hang out, meet some of the cool techie, funny animal people that you see around you. If you're not part of the Discord, we have a Discord. Join our VRChat group. You can request to join. We'll approve it. Otherwise, everybody, thank you so much for your time, and thank you for showing all the love. All right. So take care, everyone, and have a great day. I'll be here to hang out for a while longer.
And
Oh,
to answer your
yes.
question before the Q&A start.
Good to see you again. It's been a little
depending
while.
on
I finally cleaned my floor
what
again.
is food safe. You need to use food safe materials if you want to use it too.
It's a casual event. We don't really need to be too serious about it. Like we got to be on top of our stream schedule, but for this, that's why